For all of you that are here to join us, bring up chairs as close as you can to the front so you can see the monitor. And Dr. Seidel is waiting for us. Let me just give you a quick introduction. I've known him since quite a long time. Dr. Seidel's children went to the JFK school, so that's also how we got to know each other initially. He worked here in Berlin for a while with the Max Planck Institute. He's worked at LSU, Louisiana State University in Baton Rouge. And now he's a professor of physics at the University of Illinois in Urbana-Champaign. And he's also the vice president for economic development for the 3 universities that make up the University of Champaign. So we're really happy that he got up very early in the morning. It's like 7:15 there. Him and some of his staff and some of his people that he knows there. And anyway, Dr. Seidel, can you hear us?
Yeah. How you doing, Chris?
Okay. So can we all maybe just kind of give a little applause? Okay, take it away.
Okay. Thanks a lot, Chris. And good morning. It's very early in the morning here. I used to live just down the street from where you are sitting right now, and one thing you probably may not realize right now is that you're part of a community at the JFK Schule that's going to be part of your lives for a long time, and certainly I'm kind of a testament to that now. About 20 years later, I forgot, no, how long ago? 15 years ago, I guess, I moved from Berlin to Baton Rouge, and the school is still part of my life there. So it's a really wonderful place, and I'm really pleased to be able to give you a talk about something that I've spent most of my life on, which is black holes and Einstein's theories. And as you see there, I used to be at the Max Planck Institute for Gravitationsphysik in Potsdam. And Potsdam is really, I would say, the world center for this kind of work. The entire institute is devoted to the study of Einstein's theories. And I hope you've heard that in the last couple of years, there's been an absolute revolution in this field. And I'll get into that in a minute. So if you take a look at that picture where it says Physics Today, the secret story of a momentous paper, and that the swirls of the colors there are showing things called gravitational waves that were emitted when 2 black holes collided. And I'm going to tell you kind of all about the background of that and a little bit about Einstein's theories. And I'm also I'm happy to have questions at any time. So this is like mind-bending kind of stuff. It's really cool, and I hope you'll find it exciting. So let me give you a preview. Like, what is all this about? Why is there so much going on right now? So, well, if you're from Berlin, I guess most of you are from Berlin or have moved to Berlin, you should know that Einstein actually lived there. In fact, there's a place called the Harnack House just up Kleallee, where Einstein had an office, and he worked very hard to come up with his theory, his general theory of relativity. He had 2 great theories. In fact, he won the Nobel Prize, not even for relativity, but for something totally different called the photoelectric effect. So he was a great scientist, had led to many revolutions, that is, his ideas in modern science. But he unveiled his theory of general relativity at Unter den Linden at the Prussian Academy on November 25th, 1915. And that really started a modern science revolution. Another thing, he was very, very thoughtful, and so one of his quotes, which I really like, is "Imagination is more important than knowledge." So I would take that in. All right, so now, 100 years later, I mean almost exactly 100 years after he unveiled his theories, suddenly there was this great news, and there were newspapers, CNN, the BBC, the News Gazette in Champaign-Urbana, and it talks about NCSA. I'll get into NCSA. That's the National Center for Supercomputing Applications, where we are right now. It's one of the world center for the applications of supercomputing to do all kinds of science, but particularly it had a lot to do with the ability to solve Einstein's equations to predict what would happen when 2 black holes collide. So I'll get into that. Also, excuse me, in Berlin, of course, many of you, I'm sure, are reading this every day, the Morgenpost. And so on the cover, there was last year it talked about this is the discovery of the year. And so, in fact, that picture, those gravitational waves, I'm really proud of the fact that came out of my research group at the AEI in Potsdam. So, This was also the announcement of the discovery of gravitational waves 100 years after Einstein had predicted them by Gabriela Gonzalez, who was the LIGO spokesperson at the time, who was also a friend of ours and was a professor at Louisiana State University, where I had gone as well. By the way, I have some of the research group here as well. People you can't see in the corner here, but do you want to say hello? So, Gabrielle. So we have a small audience here as well. Okay, so let me now go back in time a little bit. So that black hole, there were those two black holes that collided that we discovered the gravitational waves from, actually collided 1 billion light years away. So a light year is like 6 trillion miles. So we're talking about billions and billions, of 1 billion light year, so it's 1 billion times trillion, so like, I don't even know how much that is, so it's unimaginably far away. So it took 1 billion years for the signals to get here, and so let me show you a movie. This is, I hope you can see this now. There should be this movie. This is a simulation on a supercomputer, and you see these two black holes here. So there were these two black holes. You might wonder, how do you get two black holes there? Well, they were once very big stars, and once the stars burned up all of the nuclear fuel, so stars start off with a lot of hydrogen in them, and then they burn that up and they make helium, and then the helium burns, and you get carbon and oxygen, and you get things, and eventually it runs out of nuclear fuel, and the whole star collapses. And sometimes you have two stars, like in our own solar system. We have the sun and we have many planets, including the planet Jupiter. Jupiter is the biggest planet. If Jupiter were a little bit bigger, it would have formed a star itself, and we'd have two stars going around each other in orbit. And so that's what's happened in many places in the universe, and in this case, 1 billion light years away, there were these two black holes going around each other. And I'm going to start the movie, and this is the result of a simulation where people have solved the equation that Einstein gave us that govern gravitational physics, and that's what led to this movie. So hang on. Let's see. Whoops. Oh, hang on. This is going to start. Here we go. So you'll see it's kind of choppy, but these two black holes are going around each other, and the stars behind them, they're moving, they're kind of dancing around kind of as the two black holes spiral in and they collide. And that's because light is bent by a gravitational field. And so as the field changes, when the black holes are going around each other, the stars appear to move, but they're not really moving. They're just moving through this changing gravitational field. So I'm going to explain that in a few minutes, but I just wanted to show you this. Now imagine this was 1 billion years ago. So that signal that comes from that, and so it turns out gravitational waves will come, and I'll explain them in a minute, but this burst of gravitational waves comes when two black holes collide, and they travel at the speed of light, and they had to travel for 1 billion years to get to the Earth. So think about this. When those two black holes collided, there were no people. In fact, there wasn't even multicellular life on the planet Earth at the time. So these waves are coming towards us, and life is evolving. And life is evolving, and then you get more and more complicated things, and then you go through dinosaurs, and then they die out, and the waves are still coming towards us. And then almost 1 billion years later, Einstein is born, and then he comes up with this theory. Nobody can understand the theory for 100 years, and then they eventually do. They build these detectors, and just as soon as they turned on the detectors, as soon as they turned them on in the most advanced form at the time, they detected these gravitational waves. So they just barely made it. You think about this. There's a race. These gravitational waves are coming, and humans are getting more and more advanced, and then eventually they turn on these things and they just see it. If they missed it, those waves would have gone past us, and we'd never know that these two black holes just collided. All right. So, that's just the preview. So now let me back up and explain a little bit about what Einstein did. And it sounds very complicated, but the main thing to take away from this talk is that Einstein's theories are based on very simple ideas. So, the first of them I'm going to tell you about is special relativity. It's one of the many amazing science contributions that Einstein made, but he realized that if you're in a moving frame of reference, let's say you're in a train, and you're in a perfectly smooth train, and it's moving, say, 100 kilometers an hour. If you're in that train, and let's say it has no windows, and it's just moving exactly at a constant speed, you'd have no idea you were moving. You'd have no idea. And if you're standing on the side of the road, and you're the side of the train tracks, and you watch that train go by, you yourself aren't moving. And so if you're not feeling you're moving in the train, and you're not moving sort of if you're out of the train, then Einstein said not only does it feel the same, but the laws of physics are exactly the same in both cases. Okay? So, okay, that sounds reasonable, right? Sounds reasonable. But there you add that to another fact, which is that it turns out that the speed of the light is also the same whether you're moving towards, like say, a flashlight, or if you're not moving towards it. Now, this was known because the equations that describe the propagation of light don't account for how fast the source is moving. So there's kind of a puzzle to people in the 1800s, like, how could that be? So Einstein said, okay, I'll take for granted that the speed of light is the same regardless of whether you're moving towards it. So think about it. Let's say one of you had a ball, and you're going to throw it to me. All right. So you throw it to me, and I catch it, and you throw it. Let's say 10 kilometers an hour. It's a nice easy pitch. But let's say I was in a train coming at you at 100 kilometers an hour, and you threw it at me. Then you would think that I would measure the speed of that ball to be like 110 kilometers an hour, and that's true. But if a light beam is coming at you, it turns out it doesn't come any faster towards you. And so how can this possibly be? It seems like can't possibly be true. So you take a very simple idea, and you realize something strange is really going on. And so Einstein thought about this. He realized it. And he said, the only way that could be would be if you're in a moving frame of reference. If you're moving, then you must measure distance and time in a different way, because the speed is constant. So its speed is distance divided by time. So if you're moving in a moving frame of reference, that has to change in some way so that the speed of light is the same. Right? So, because speed of light is how far does light go, in a second, divided by a second. That would be the speed of light. So, that's the only way this could be true. And so Einstein worked out, in fact, an entire theory, looking at a set of equations that describe the propagation of light, and said, here's the formula. I won't show you the formula, but the point that he came up with was that moving clocks have to go slow. So, if you're in a train that's moving, so that's the lower clock there. It's going slower than the one above of the person standing on the side of the road. Now that seems like crazy, but it's been verified and it's true. So Einstein made this prediction. He thought about it, worked it out. It's exactly what happens. So the second thing that happens is that moving clocks go slow, but moving rulers actually shrink. Now that seems... I thought about this for years. How can that possibly be true? But it is true. So if you're measuring, you have a ruler, it shrinks. If you're moving, everything shrinks in the direction of motion. So it gets shorter, and it sort of gets like contracted. And this leads to all of these strange paradoxes. So one of them I'll let you think about. Let's imagine that there are some robbers by a tunnel of a train, on a train track, and a train's coming. And the train is coming really, really fast, like almost relativistic speed. So it turns out you don't notice this in daily life because the effect is so small, you just wouldn't see it. But if you're going almost the speed of light, that's really fast, then these effects can be very pronounced. So robbers think that they're going to catch a train, but the train is actually, like if the train were sitting next to the tunnel, let's say that the train might be twice as long as the tunnel. But if it's going really fast, it'll look to the robbers like the train is very short. So they think they'll just trap that train when it gets inside the tunnel. And so the question for you to think about is, can they trap the train in the tunnel or not? Is it really shrunk enough to fit in the tunnel, or what? How can that work out? And it turns out they can. It turns out they can trap the train in the tunnel, but you have to think about that. All right. So why haven't we noticed this? We haven't noticed it because we are going too slow. if you're going almost the speed of light, like 9/10 of the speed of light or something like that, which we never do in our real lives, it's so fast. The speed of light is 3 times 10 to the 10 centimeters per second. So in miles, I think it's 186,000 miles per second. So if you're going anywhere near that speed, you'd notice these things all the time, and this would all seem natural to you. But if you're going like just on terrestrial speeds, it's very slow. All right. So special relativity says basically all times and distances are relative. That depends on the relative motion of people or objects with respect to each other. All right. So that's physics lesson number 1. Normally you spend like a couple weeks studying that, so I just compressed the basic idea into one slide. Okay. So Einstein came up with this. It was amazing. And then he felt like it wasn't enough. He wanted to understand, he wanted to figure out gravitational physics as well. So he thought about this for 10 years. I mean, he really worked on this for 10 years. What happens in a gravitational field? And he came up with this idea that's called the equivalence principle. And he says, okay, just like if you're in a train and it's moving at a constant speed, if it's accelerating, you'll feel it, right? But it's moving at a constant speed, then you won't feel it. And he says, okay, the laws of physics are exactly the same in a moving train as they are along the side of the tracks. He said the same thing about a gravitational field. He said it's just like an acceleration. So he says, like, if you're in a rocket ship and it's accelerating, you'll feel yourself like pushed back in the seat, right? So I don't know if you can see me, but I'm pushing myself back in the seat. And so you'll feel that. Like if you're in a car and the light turns green and you hit the gas, you'll feel pushed back. So that's an accelerated frame of reference. Einstein said that's exactly the same as a gravitational field. I can't think of any way you could tell the difference. So therefore, I postulate that they are exactly the same. So it's like Newton's apple, the apple falling out of the tree. That's the same as a gravitational field. It's the same as an accelerated frame of reference. Okay? So I have another thought experiment for you. Let's say you're in the car. So you're on Telto or Dom, and the light turns green, and you accelerate, but you've got a helium balloon in the car. Okay, you have a helium balloon that's just sitting there in the car, and you accelerate. Which way does the balloon go? So you get pushed back. You have to think about it for a second. So I'll give you the answer. So counterintuitively, the helium balloon will move forward in the car when you accelerate. Now, why is that? Why is that? Because if you're accelerating forward, it means it's exactly the same as a gravitational field pulling you backward. And as you know, if you let go of a helium balloon, it goes kind of against gravity. It goes up because of the density of the air. So it creates a gradient in the density of the air. So a helium balloon will go forward in the car. So I actually once got into a car and I tested this just like to see, does it really work? And it does. And so that illustrates the equivalence principle of Einstein. Okay, so this seems okay. So it seems kind of simple. Okay, but it has consequences. Has amazing consequences. So one of them is the bending of light. So until Einstein came up with this, no one had the idea that light would be bent by a gravitational field. So it's like the light particles are attracted by a gravitational field. And you can think about it just in terms of an elevator. So if you're in an elevator, look at the left-hand picture there. You're in an elevator and you're going up at constant speed, and you have a flashlight and it emits a light beam going across. Okay, it won't. It'll just kind of go along with you. But if you're accelerating, then the elevator kind of accelerates. It accelerates kind of underneath the photons, and the photons will actually then, since they're going straight across, it'll look like they're falling down. If you follow that logic. And so therefore a gravitational field will attract photons just like anything else. And so light is actually bent by a gravitational field. So that's sort of the logic behind that. Now this is the most mind-bending of my thought experiments, so you got to stick with me on this one. Okay? So Einstein, this is actually in his original paper, where he thought about somebody on a merry-go-round, and he thought about 3 different people on the merry-go-round. Thought about the attendant that's sort of standing by the side, so just watching the kids so they don't get hurt. And then there's somebody at the very center, and then there's somebody going around and around at the edge of the merry-go-round, okay? Or maybe if you go to an amusement park, there's a thing called the rotor. You know, sometimes you're in like this room and it's going around really fast, and then you're up against the wall, and then the floor goes underneath, and you're sort of pinned up against the wall because you feel the centrifugal force pulling you, pushing you back, right? So you feel that. All right. So let's think about how these three different people experience physics. Okay? So the first thing you'll note that the attendant is standing still, but the person B that's going around and around, well, he's moving relative to person C. So therefore, person B's clocks are going slow compared to person C, right? We just established that. If you're moving relative to somebody else, your clocks are going slow compared to them. Okay? But A and C are not moving with respect to each other. They're the same distance from each other. They're not moving at all. And so therefore, their clocks go the same speed, A and C. Okay? Right? So think about that. So that means that B's clocks are going slower than A's clocks. But they're not moving with respect to each other the same distance or the same distance, right? So, but there's a difference because person B is in an accelerated frame of reference because they have this force, this centrifugal force that's pulling them sort of out. So if it went fast enough around, that person would just get spun right off, right? So that means, and since they're accelerated, that's the same as a gravitational field. That means a gravitational field slows down time. So it really means that a gravitational field actually slows down time. Another thing is think about the rulers. So ruler A compared to C is the same, but B's ruler is contracting, right? So therefore, you have the same logic there. So it turns out that the ruler of person B actually gets contracted relative to person A. And so the only difference is person B feels that they're in a gravitational field, but person A doesn't because they're just sort of sitting in the middle there. So that means that gravity actually changes clocks, it changes time, and it changes the geometry. So like, you remember that you've all at least know that for a circle, pi is the circumference divided by the diameter. So these measurements depend on whether or not you're in a gravitational field. So that means geometry actually depends on the gravitational field, which seems it seemed like it couldn't possibly be, but because we never noticed that in our real lives. But if you're in fast-moving environments or strong gravitational fields, you would notice these things. So clocks in a gravitational field slow down, and gravity warps space-time. So space is curved if you have a gravitational field. So just two little thought experiments. You go home and think about it. Think about clocks in a plane. So do they go faster or slower than clocks on the ground? So I'm telling you, they go slower. And you can actually put a clock in a plane and fly it around and then measure. If you have an accurate clock, you can measure that it actually goes slower. Or think about clocks on top of a mountain. The further you get away from the Earth, from the center of the Earth, the weaker is the gravitational field. So you can measure the speed of identical clocks, like on the ground or at the top of Zermatt, and you'll find the one on the top of Zermatt is going slower than the one in Berlin because it has a weaker gravitational field. So these are verified. It's amazing. All right. So, one more little physics lesson. This one's a little bit easier, but so why do things move? Why do things move as they do? So, first of all, looking at this train track, in a flat space, those two parallel lines stay parallel forever. But if it weren't a flat space, parallel lines and geometry changes, and that's basically, so flat space in this context means no gravity. But if there's gravity, then it does actually curve space, and so therefore our geometry has to change. So Einstein made another mental leap. He said, well, if gravity just warps space, if that's what it does, then if something's moving, it's got to move in that warped, curved space. And so maybe gravity just changes the path of an object by changing the geometry that it's moving through. And in fact, that's what it is. So while Isaac Newton says, the force between two objects is this, F equals ma equals, the product of the two masses divided by r squared, that's the force between two objects. Einstein says, yeah, okay, that's right. But here's another way to look at this. Mass curved spacetimes and objects move in the shortest possible path in a curved spacetime. So, simple idea. Remember, how simple is that? It moves in the shortest possible path, but it's a curved spacetime. So, how might that work? So, if you're in a just Euclidean geometry, like the geometry you learn in 10th grade, the shortest path is just a straight line in a flat space on a plane. But on the curved surface of a ball, the shortest path is curved, isn't it? You can't, so that's what's known technically as a geodesic. And so that means the geodesic just means it's the shortest path in a curved space. So Einstein says you can think of all gravity as simply changing the way objects move because the space they're moving in is curved. And so that then explains how a ball moves, how the Earth goes around the sun, and so on, by curving space-time. And again, these things have been measured. So those are the basic physics lessons. You can learn more. I'll give you some references later to learn more about that, but that's the idea. Okay, so collect those ideas. Any questions? Shall I stop for some questions?
Do we have some questions for Dr. Seidel? If we do, really, call him out. It's fairly informal. Any place you'd like to know more at this point or that he might have lost you?
So I just crammed a semester of university physics into about 10 minutes. So there might be some questions.
Yeah.
Okay, well, you can save them. Or is there a question?
Got one. Hold on. Yeah.
Okay.
Time if gravitation's bent time, then technically speaking, time would be different everywhere in the universe at different times, right?
So if gravity bends time, then technically time would be different at every place in the universe?
Yeah. I mean, it depends on the gravitational field, but yeah.
Could you, through this knowledge, manipulate time in a way that we could make it so slow that it technically doesn't move at all?
So could you manipulate time with this idea and make things go so slow that in fact time wouldn't pass at all?
You could if you could change the gravitational field. So how many of you seen the movie Interstellar? So yeah.
Yeah. About more, yeah.
So there's a lot of that kind of thing going on in Interstellar, and I'm going to come to that in a minute. But there's also a book called The Physics of Interstellar. So the guy who was behind that movie Interstellar is a guy named Kip Thorne, and he had a contract with Hollywood that says every scene in this movie has got to at least not violate any known laws of physics. And he wrote a book explaining every single scene in the movie, how it could work with general relativity as the major sort of science behind it. And it's written at the high school level. I mean, what Kip thinks is the high school level. I would say I've read the book, and I had to struggle through some sections of it, but it's something you could read. It's amazing. Anyway, I'll come back to that.
What was the name of the book again?
It's called The Science of Interstellar by Kip Thorne.
The Science of Interstellar. Got one other question before we go on. If you could take a ruler and put it out where there's no gravitational waves, like outside the universe, would the ruler stretch out?
So I'm not if you're out. I'm not sure what you mean by outside the universe, but the universe. So as the universe expands, of course, rulers will expand too. So because space itself is actually stretching out.
Come on up. I'm going to let him ask you directly, Dr. Seidel. Hold on.
Okay.
Since you told us that the more or the higher the gravitational power is, rulers start to shrink. And now if you would just switch that around and practically put a ruler outside of the observable universe, let's say without any gravitational forces acting upon it, would it like stretch into an infinite amount?
No, I see what you're saying now, right? No, so the idea is that let's say you build a ruler in the absence of a gravitational field, and it's like a meter long. If you put that by a black hole, it would, from your point of view, it would appear to be less than a meter long. But no, it wouldn't. It's not like the gravity is needed to keep the objects from sort of going out to infinite size or something like that. So I think I understand your question now. So no, it wouldn't expand like that. Okay. So
Any other questions before we? Okay, I think Dr. Seidel, we're ready to continue.
okay, good. So I talked earlier about a black hole because everybody's heard of that. Well, let me tell you a little bit more about what a black hole is, and then we'll get into something about the gravitational waves. So the black hole, in the kinds of black holes that we're seeing in things like the popular in the modern era, when you see in the newspaper about colliding black holes, these are basically from big stars that eventually ran out of nuclear fuel and they collapse because gravity is pulling them in. They run out of fuel, so they get cooler and cooler, and therefore the pressure that they would have to sort of support them against gravity goes away, and gravity becomes so strong. If a star is big enough, it has to be above a certain mass, like several times the mass of the sun. So like a star several times bigger than the sun would eventually collapse down to a black hole. And so how does that work? So first of all, once a star is collapsed to a black hole, the gravity becomes very, very intense. And the reason it becomes intense is that there's more and more mass in a smaller and smaller volume. So you can get closer to it, if you see what I mean. Like if you're on the Earth, you feel like we're all on the surface of the Earth. If the Earth collapsed down to a point, it wouldn't make the gravity where you are any stronger. It'd feel the same. But then you could get closer in, and you'd feel it would be more and more powerful because the same amount of mass is concentrated all the way down to the center of the Earth. And if you got closer into it, you'd feel it more and more strongly. So you'd feel the stronger and stronger gravity. And at some point, if say a star that's say 10 times the mass of the sun, it collapses down to a point. If you get close enough to it, the gravity becomes so strong that light, which I told you earlier is bent by a gravitational field, the light is actually trapped and it can't get out. So that's what a black hole actually is. So I've shown this picture where there's like a spaceship and there's a black hole there, and the astronaut was out doing a spacewalk, and it gets kind of pulled into this black hole, and he's eventually, and there is something technically wrong with this picture. I won't explain it, but if you're inside the black hole, you can't get a light ray out. So in fact, in this case, the astronaut's inside the black hole, and he's calling for help, and his colleagues in a spaceship can't hear it, and so it would never be able to. Because no signals can get out from where that guy is standing. He's inside what's called the event horizon of the hole. Now, just outside the black hole, it says escaping light and gravity waves. There you can get signals to go away from it, but inside a certain a boundary, you can't get any signals to come out. And so that's kind of what I call the anatomy of a black hole. If you're inside it, you can't communicate with anybody on the outside. That's why it's called a black hole. But if you're just outside it, signals can still get out. So there's like this critical boundary where you can imagine, you have enough energy that you can just get away, but if you're a little bit closer, you're trapped. And that's the boundary called the event horizon of the black hole. All right. So one more lesson here then in terms of another thing predicted by Einstein is gravitational waves. All right. So what are they? So Einstein come up with this theory. A little bit later, like the next year, he's like, wait a minute. This thing predicts that my theory predicts that there are these things called gravitational waves. And so no one expected these things. Einstein didn't think they could ever be detected because they were so weak. But in any case, he predicted that there were these waves. Now, what are they? Well, you've all heard of electromagnetic waves. It's light. So we're seeing light. I see light coming in your window. I got lights on here. And basically light comes when you have a charged particle, like an electron, and it moves back and forth. Let's say for some reason it's in your light, you have electrons moving around. It heats up the material, or it's just directly emitting light because electrons move. And then when it turns out, just in a nutshell, if you move an electron back and forth, you get electromagnetic radiation that comes out and you get light. So Einstein said if you take a mass and you move it around in a certain way, it turns out certain modes don't emit waves, but it doesn't really matter. The point is, if you shake a mass around, you get something just analogous to electromagnetic radiation. You get gravitational waves. And so it turns out that you get more waves if you have faster motion or it's more irregular. Or more massive. Those are the sort of qualities that give. I won't go into the theory, but so if you wanted to actually ever see anything like this, the strongest sources of gravitational waves should be like cosmic cataclysms, like a star explodes. That's called a supernova. It explodes. So something like, say, 5 times the mass of the sun explodes violently in a few milliseconds. That actually happens. So a supernova emits more light, like a single star in a galaxy. When it blows up, it emits more light than all the other stars in the galaxy combined. To give you an idea, it just boom, in this big burst of light, and gravitational waves come out. Or if you have colliding black holes, things that are like 10 times or 30 times the mass of the sun, they're black holes and they collide at almost the speed of light, that would emit a lot of gravitational waves. So these are this is why you look for these kind of events in the universe to produce gravitational waves that you might actually detect. Otherwise, they're so weak. And Einstein didn't know about black holes, and he knew about supernovae, but probably hadn't really thought about them in this particular context, and so thought we would never, ever be able to detect gravitational waves. So look for black holes. All right. So then 20 years later, Einstein got confused. This is really true. And so a lot of people are very confused by Einstein's equations and his theories and so on, including Einstein himself. And after about 20 years after he published this, he tried to write a paper saying, actually, I don't believe in gravitational waves anymore. I think that I was wrong. And amazingly, the paper he wrote was rejected by the the science reviewers that reviewed the papers of Einstein, who was already famous, won a Nobel Prize and everything. And it turned out he was wrong. He was wrong that he was wrong. So he retracted his retraction, and it turns out, yes, they are real. And we've now discovered them. So to give you an idea, if you think this is complicated for you, Einstein himself was confused by all this. All right. So what happens? What is the effect if you're hit by a gravitational wave? So it turns out it makes time and space vibrate. So when a wave comes through, like gravitational waves are coming through your classroom right now. They're coming through all the time. And they're causing your bodies to stretch and squeeze in a certain way, but it's so minute that you will never detect it. But that's why you see that picture there. That's one of the gravitational wave detectors that detected the signals from colliding black holes. So it's about the size of, Telto or something like that. It's about 4 kilometers. Each of those arms there that you see in that picture, there's one going off to the left kind of in that picture. That's an arm where there's a laser beam bouncing back and forth inside a tube. And what happens is that laser, the arm length of a gravitational wave comes, it gets smaller and it gets bigger. So it sort of contracts like this. Not exactly like that, but I didn't have a PowerPoint that could do exactly the right motion. But it does sort of get squeezed and stretched. And so if you do timing of the laser beams that are bouncing back and forth inside that long tube, and it gets the arm length gets changed a little bit because it gets stretched out or it gets squeezed down, that changes how long it takes the light to go all the way across that tube and back. And so by allowing the 2 light beams, there's also one going off to the right. So it turns out the one going off to the left gets stretched and the one going off to the right gets squeezed. And so if you let the light beams interfere, you can tell that the entire apparatus is oscillating. So that's the basic method for determining gravitational waves. And so there is there's a detector in Hanover, just off to the west of Berlin. One of the main detectors in the world is called the GEO 600 detector, and it's run by the Albert Einstein Institute. And that's where a lot of the advanced technologies that they're developing for these things are developed. So there was a big debate for a long time. Einstein wasn't really sure if they were real, gravitational waves. There was a great scientist also named Eddington who didn't believe in them at all and had this famous physicist quote saying, "I don't believe in gravitational waves. Gravitational waves propagate at the speed of thought." So he thought that was nonsense. And so this is what 100 years later was actually detected. And so this leads to this basic idea of science that if you have an idea, even if it's crazy, it has to be fundamentally experimentally verified to be shown to be true. It's not fake news. It's actually verified, and it was real, although people didn't believe it for a while. And that's what happened. That is, a couple years ago, those waves were actually detected. Okay. Well, let me tell you another little thing about this theory. So you see this whiteboard, the blackboard, sorry, we use whiteboards now, but blackboards in those days with chalk. So Einstein is working on these equations, and they're so complicated nobody can solve them, including Einstein. And he had a great quote. He says, "Do not worry about your difficulties in mathematics. I can assure you that mine are still greater." And so he had this theory that is based on really simple ideas, but the mathematics were really complicated. That's one thing that took him 10 years to work out. So we had to get help from some mathematicians in order to understand how to build his theory out of mathematics. But the equations are really hard, and they're very complicated. So this is an old slide that I had that shows you these are partial differential equations. So you might have, if you're studying calculus, you know how to take a derivative of a function. So partial derivatives mean in multiple dimensions, it's more complicated. And this is like page 1 of some of Einstein's equations, and page 2, and page 3. And they're so complicated, you can't solve them. Einstein, nobody could solve them. This is one thing that hindered progress. Okay, so you can't solve the equations, and you can't detect gravitational waves. That's what Einstein died thinking that, basically. You'll never solve these equations, and you can't detect them. So it was, I'm sure he was happy with what he did, but it was a little frustrating. So a century of work using supercomputers and advanced technologies, and they both came together last year, 2 years ago, to actually detect the gravitational wave. So let me tell you a little bit about the computing side of this now. So it turns out that both Illinois, here where we are at NCSA, the National Center for Supercomputing Applications here in Urbana, Illinois, or Champaign. I guess we're in Urbana, and Berlin have both played a major role in solving Einstein's equations. So this entire computing revolution actually, in many ways, came out of Berlin. You may not realize that, but there was a great scientist, Konrad Zuse, and in fact, there's just up on Animale, I think it is, there's the Konrad Zuse Institute, and it's just, it's about 2 kilometers from the JFK Schule. And so, in fact, that institute is there by name to honor Konrad Zuse, who really was the first to have a functioning electronic computer. And so, in fact, I was in Berlin a couple years ago to give a talk to commemorate the 75th anniversary of the invention of the computer. So that invention has clearly impacted the world more profoundly than any other in modern times. So the invention of the computer, and it came out of Berlin. And then you've also got Einstein coming up with the most revolutionary theory of the 20th century. So they both came out of Berlin. It's amazing. So meanwhile, there's a guy here, an American named Larry Smarr, who was actually trying, for his PhD thesis, was trying to solve Einstein's equations for colliding black holes. And he was studying this problem. He didn't have enough computer power because the equations were so complicated. So in fact, he would go to Germany, to the Max Planck Institute, not in Potsdam, but one in Munich. There wasn't one in Potsdam at the time. And they had the only academic supercomputer available. And so he used that to do his work on black hole collisions. And he was so frustrated that he wrote a proposal to the National Science Foundation in 1984. and said, we have to have supercomputers in America just like the Germans do. And that's what led to the founding of NCSA and an entire series of supercomputing centers in the United States that started the revolution of computational science, I would say. But it was inspired by exactly this problem of Einstein. He needed a lot of computer power to do his work on colliding black holes. And so NCSA has just had its 30th anniversary, actually, the year before last. And so it's 3 decades in. So there are a lot of anniversaries going on now. And so we now have, this is a picture of the building that I'm in right now. I used to be the director of this center, but I'm now, I'm just over here with friends who run the center. And do you see that computer in the bottom? That's called Blue Waters. That is the biggest supercomputer in the world, at least at an academic institution. And it has about a 500,000 processors. So you see how big that is? That building on the left, the upper left, that's a building built specifically just to house this supercomputer. And so that computer is used to solve all kinds of problems in astrophysics, like colliding black holes, and biology, like the structure of DNA and all kinds of things. All right. And so now we have this science of gravitational waves where some object in the universe, in the upper right-hand corner there, you see those 2 black holes, they're coming together, gravitational waves are coming out, and they come to the Earth, they're detected by those observations, those observatories on the left, and then they compare. What do the computers say the signal should look like? What's observed? And then you can observe it and you say, what does the computer tell me? The computer tells me that was 2 black holes of 30 solar masses each that just collided at the speed of light. And then you work out, that was out that way, a billion light years away. So now there's this science going back and forth between the supercomputer calculations and the observations that are going on. And so there are 2 detectors in the United States that they cost about $1 billion to build those detectors, and then there's a smaller one in Germany that's used to develop the advanced technologies that they put in those detectors. All right, and so basically that's what you get. You get a signal. There are like these different phases. During the period when the 2 black holes are going around each other, then they spiral in, and there's the so-called chirp, and they merge, and then they form a big black hole that's just oscillating, and that's the final stage called the ring down. It's like you hit a bell, the bell rings, and it decays away. It's like bong, and it goes down like that. That's the final stage of the black hole collision. All right, so then, 1 billion years ago, those 2 black holes collided, those waves came to us, and then they were detected on September the 14th of 2015. I mean, literally within 2 months of being exactly 100 years after Einstein found his equations, this happened. And so that just was really exciting. These were the signals that were determined, that were observed compared to the observation. So the top signals are what were observed in those 2 detectors, one in Washington State and one in Livingston Parish in Louisiana. And then the middle graphs are what were predicted by supercomputer calculations of 2 black holes that collided, one of about 30 times the mass of the sun and the other about 35 times the mass of the sun. So it's incredible that this all happened. So newspapers around the world show it. This is the sort of announcement of the gravitational waves. The guy on the right there is Kip Thorne. He was actually the thesis. He's at Caltech. He's the thesis supervisor of a guy named Bernard Schutz, who was the director of the Albert Einstein Institute in Potsdam, whose daughter Rachel went to school there and was great in the musicals. Now is an opera star. Just to bring it back to you, back to the school. The guy on the left there is a guy known in America as Ray Weiss. Also the same name as Chris. He's from Berlin. He grew up in Berlin, moved to America. He also won the Nobel Prize. So these 2 guys and a third person shared the Nobel Prize for this discovery. And so there you go. On the Berliner Morgenpost, it says the Physics Nobel Prize was announced and so on. So, okay, yeah. So that's a picture of somebody at the Albert Einstein Institute in Potsdam. Like, that's the hallway. My office used to be just down the hallway right there. And so, okay. So the point is that this is now this new era of science. It's not just one discovery. It's discoveries all the time. So New York Times, scientists hear a second chirp from colliding black holes. Now another one, I forget what that's from, but gravitational waves from black holes were detected for the 3rd time. And then, oh my gosh, neutron stars now collided, and that was discovered last year. And so it's just happening all the time. Amazing discoveries every single month practically. And so we're entering a new era of science where you'll be able to combine neutron star science and black hole science and electromagnetic observations with gravitational wave observations, and it's a new era. So the breakthrough of the year a couple years ago was the colliding black holes. This year, Newsweek says it was colliding neutron stars. I didn't have time to get into that, but it's sort of like a failed black hole, but it creates a bunch of neutrons, very dense, different kind of physics, but similar collapsed objects, and then they can also collide. So, I hope you've seen this. This is a stamp that I don't know if it's still available, but in December, this German stamp was available to commemorate the discovery of gravitational waves. This stamp was made by a former student of mine. In fact, I forgot, from Werner Benger from the Albert Einstein Institute. So one of the great breakthroughs that allowed us to discover gravitational waves, to solve Einstein's equations, was made by Frau Ruschel's husband. So she was a physics teacher some years ago. So Kristen, you may not know this even, but her husband, Michael Kopitz, was a student of mine, and he was behind one of the great breakthroughs that actually led to the ability to solve these equations.
I did not know that.
Yeah.
Cool.
So anyway, one more slide or two just to point out the impact on society. So let me just talk about the computing for a minute. So on the left there, you have a picture of the first Cray computer. And in fact, that was the computer that Larry Smarr was doing his first work on to collide black holes. That was the one from the Max Planck Institute down in Garching, outside of Munich. So an iPhone 6, I made the slide a couple years ago. So you wouldn't even want an iPhone 6 anymore, probably, right? Because it's so slow. It's 1,500 times faster than the first supercomputer that was used to solve Einstein's equations. And now that one on the right, that's actually a computer circuit that you can actually put in your skin. And that's actually developed by a guy who was here until recently, John Rogers, here at the University of Illinois. So it's going to change the world. It's not only changed the world, we're going to have computers embedded in our bodies, direct brain interfaces, eye interfaces, everything. It's happening now. So it's going to really change everything. So if you want to learn more about all of this, let me just point out, go look this up. It turns out your GPS system, it wouldn't work without general relativity and special relativity both. It would say you think you're in Berlin. It might say that you're in Teltow if you didn't have these corrections. You have to know about special and general relativity. The web browser. The web browser was invented here at NCSA. I was here when it happened, so you can't imagine life without a web browser. In some ways, you can trace that back to Einstein's theories because they were developed, it says, based on NCSA Mosaic, Internet Explorer. Here at NCSA, NCSA itself was created to solve Einstein's equations, so that came out of Einstein as well. Another thing you might not realize is the science of interstellar. So I was telling you this earlier. That's Kip Thorne on the left. I took that picture of Kip the day of the announcement, and on the right is the scene from the movie. And so that entire movie is based on general relativity and special relativity. And so in Kip's book, you can get it on Amazon, it describes every single scene, the science behind it. All right, the last one is, there's a website called scienceface.org, and that's actually developed by Susanna Milde, who's a marketing person who works with the Albert Einstein Institute. She lives in Potsdam, and so she has this website with interviews with a lot of great scientists, including Kip Thorne and Bernie Schutz, and I'm actually in there, and a bunch of others as well. So you can learn a lot about this just with interviews. And the interviewer in these movies is actually Annalie Schutz, who was a student at the JFK Schule, who was one of Bernie's daughters. All right, so let me just summarize. It probably went on quite a bit longer than I anticipated because I get excited about this, but why not? It's a great time for science. It's one of the great breakthroughs in the history of physics, I would say, without a doubt. What we're seeing right now is the discovery of gravitational waves. Einstein was right, even though he himself wasn't so sure about that for a while, and that Berlin and even little Champaign, Illinois, have played important roles in making all of this happen. So if there's any time left, I'm happy to have questions and talk about this.
First off, I think we want to thank you. So first, It was really, really great. And I think we have a number of questions. Let me just say, I know a couple of students have to leave early, so don't be offended if you
Sure.
see a couple sneak out the back. They told me already. But for everybody else, let's ask some questions. I think I'm going to have you come up and ask questions from here. I'll get out of the way because you're going to be better at explaining your question than I will be trying to translate it to Dr. Seidel.
Okay.
So just come on up one at a time. Come on up. And I've got a couple too, Dr. Seidel, if we
Okay.
run out of some.
Two questions.
Please, go ahead.
The first one was about the event horizon with black holes. You said it does apply to light, but it also applies to gravitational waves.
Yeah.
Now, my question was, since we have found out that we can more or less attract light somehow, we can bend it through gravitational waves or just gravitational fields. We haven't really found out that gravitational waves, you can actually bend them somehow, and you can also, since you can make light, or you can describe light as a photon, you can't really do that with gravitational waves. So what would actually happen to a gravitational wave if you would pass, if it would pass through a black hole?
So gravitational waves also have we have a photon, which is the particle of light, and so gravitational waves would have a thing called a graviton, which would be like the particle of gravitational waves, just like we have in electromagnetic. So they're similar in that sense. They have slightly different qualities in terms of like how they spin and so on, but that's kind of a technical thing. So they have the same kind of physics. They both are supposed to go at the speed of light, but we have to actually measure that. So with this discovery of gravitational waves and also of the fact that, say, if neutron stars collide, you can also see them in electromagnetic radiation. You can then do comparisons of when the signals arrived and then try to figure out if gravitational waves really do travel exactly at the speed of light as predicted. And so, I mean, so far within the accuracy of measurements, they do. And you can, so they behave in a similar way. Gravitational waves are also bent by gravitational fields, just like light would be. And so another question that you might ask is, if black holes are sort of preventing anything from getting out, how can we see signals from a black hole? And the answer to that is that there are regions just outside the black holes that are responding to all the gravitational field of the black hole that sort of and they can be very dynamic as the black holes are colliding. So there are these like hot spots just outside the black holes that then also vibrate and emit gravitational waves and electromagnetic waves, and then some of them go into the black hole and will never be seen, and others actually come towards us. So there's a way out of that sort of apparent paradox.
Okay, thank you.
Okay.
Hi. First of all, thank you so much for your talk. And I was wondering if we have predictions on how often inside the observable universe such big events happen that they create like such huge disturbances in the gravitational field.
So they're happening all the time. So it depends. If you looked at the entire universe, I don't know. Maybe someone here knows what's the predicted rate of like black hole collisions. But with the next generation of the gravitational wave detectors, so they're improving them right now. They'll be a little bit more sensitive when they're turned back on again this next year. They'll be able to see events like this probably like every week, something like that. So. Sorry, every 15 minutes, I'm told. So every 15 minutes we may be seeing signals like this with the new detectors, and so that'll go up as the detectors get even better and better. They're going to eventually put some detectors in space, and those will have a different sort of frequency range. They'll see much lower frequency waves. So yeah, it's happening all the time. I mean, like all the time, things like this are happening.
Thank you.
Hello, thank you for giving us the talk. I have two questions. My first question would be, considering that gravitational waves make time-space vibrate, would you technically be able to see things that shouldn't be able to be seen? For example, as far as I know, seeing things, it's only a reflection of what light gives you, so light bounces back to your eye and you see that. Let's just say that you could bend light in such an extreme angle that something that, or light waves that have already passed you come back to your eyes, so you see things of the past, technically. Would that be at all possible?
So I've got a couple answers to that. So first of all, everything you see is actually in the past because it took a little while for the light to get to you. And so, when you're looking at somebody across the room, you're looking at them as they were just a tiny fraction of a second ago. If you're looking across the universe, of course, you're seeing things that happened potentially billions of years ago. And so you're always seeing in the past, but also the one thing that I can think of about seeing things that you shouldn't see, you can see things because the light has taken a curved path. That the light you might normally your visibility of that object could be blocked by something else. For example, when they did the original experiment to determine is light actually bent by a gravitational field. So there was a famous experiment or an observation that was done in Africa when there was an eclipse, a total eclipse of the sun, and Einstein predicted that the light would be bent by the sun by a little bit because the sun doesn't have that strong of a gravitational field. So that means that a star, that's the light's coming from a star, if it's like just going right by the edge of the sun, it would appear to be in a different location because the light would be bent as it goes around the sun. So you probably can't see me moving my arm like this, but so it would look like if it's just grazing the right edge of the sun, then because it gets bent around then and comes to you in the earth, it would look to you like it's off further to the right than it really is. So, or it could be like something was like behind the sun or behind like a black hole. Then you'd be able to see things behind the black hole because light that was normally going away would then be curved back towards you and you'd be able to see it and it would look like it was out there. So then it creates a kind of a lens, and you can get things called the gravitational lens effect, where you get even really weird shapes like an entire ring that's just like a single point source and things like that. So gravity can act like a lens and then really distort what things look like.
Okay, and if you'd allow, I have a second question. Sounds like it? Okay.
Sure.
According to welchen Teilrealismus? Every wave has a particle, and every particle is a wave. You know what I mean?
Wave-particle duality.
Right.
Oh, thank you. Wave-particle duality. What would the particles of gravitational waves be, so to say?
What do particles of gravitational waves?
Gravitons? Yeah. Thank you.
Couldn't quite hear it. They're called gravitons, yeah. So just like photons or like the particle nature of the light wave, same thing. And you'd have the same physics around that of the particle wave duality of the gravitational waves.
Okay. Hi.
Hi.
So I have a question. I'm not sure if this would apply to black holes, but I know the neutron stars that collided last year that we saw. Like when the physicists were measuring this, did they, I guess, alert the astronomers and tell them to point their telescopes out there? And could you actually see anything after you heard this trip? And if so, like, what did it look like?
Yeah, I didn't really explain this very well. That's what multi-messenger astronomy now is all about. So when we say multi-messenger, we mean like different messengers. So gravity is a messenger. In this way, it tells you a certain thing. And light is a different messenger. It's electromagnetic. And so it's a completely different kind of process than gravity. So it's electromagnetic waves. And so yes, that neutron star collision was coordinated between the physicists who were doing the gravitational waves and the astronomers who do electromagnetic observations in many different bandwidths, from gamma rays to through all different detectors. And so yes, that observation was made by, I saw some quote, I don't know if it's really true, but something like a third of the world's astronomers were involved in this one observation. So it was really amazing to have different groups around the world all looking at the same object. Neutron stars, so gravitational waves actually would be the first things, although actually the gamma rays were noticed actually technically first, I think is the way it wasn't, LU knows this, but 60 seconds later. But I thought that they were actually seen first. Yeah, independently, right. But so the gravitational waves come first, and then the photons come later. Is the physics of it? The way it was actually observed, I think somebody said, "Hey, there's a gamma ray burst," and then the gravitational wave people said, "Hey, there was a gravitational wave burst too," and it happened right before. And then all these other things came, and so it's observed. It's incredible what this one observation did. It's incredible.
Okay, thank you.
And you might have heard that a lot of the gold that is produced in the universe comes from neutron star collisions. So if any of you have like gold necklaces, it probably came from a neutron star collision, actually.
Quick question, Doctor. You had mentioned that any signal or object that is trapped inside of a black hole cannot communicate with sort of its surroundings.
Mm-hmm.
How come a black hole is isolated from the inside, yet permeable from the outside?
So that's a good question. It's like a one-way membrane. If you were to go inside it, you would never be able to communicate out. Although, if you watch the movie Interstellar, it's a little more complicated than that. But because quantum effects can change that, basically. But just according to classical physics, there would be no way to communicate anything out. The thing, by the way, that was technically wrong with my picture was if you're in a spaceship near a black hole and you actually try to go outside the spaceship, so that you have your friend who stays in the spaceship and he's monitoring everything. If you start to fall into the black hole, what the spaceship would see would be your time slows down because you're getting closer and closer to the event horizon of the black hole. And so from the point of view of the guy in the spaceship, you would sort of just freeze in time. You just sort of slow down, and you'd never actually cross. But from your point of view, you just cross right in there. And so that's kind of what I was saying was technically wrong with that. From the outside, you'd never actually see the person going in. But if you're the person falling into the black hole, you'd go right in, and then you'd realize you could still see the spaceship. You wouldn't be able to communicate with it though, because light goes in, but it wouldn't go out.
Okay, thanks.
So you've probably already heard about this, but like in this thought experiment, a car, say you're in a car and you drive at the speed of light, and you turn your headlights on. What would happen to the speed of the light that you shoot out of the headlights? Would it be double the speed of light, or would it be lesser?
No, that's the amazing thing. It's just the same speed. It seems impossible, but it's true. That's what Einstein realized. That means there has to be something about the way space and time actually work at high speeds. Otherwise, you'd think it would be twice this. The photons would come at you at twice the speed, but they don't. It's always the same number.
Thanks.
I have just a practical question. For example, let's say you're in a spaceship and you're moving like 1 kilometer slower than c, or the speed of light, and you would then try to throw a ball at let's say 10 kilometers per hour.
Yeah.
It would not let you throw it that fast? Would it just like start to freeze in time? What would it like happen to that ball?
Yeah, it's just it wouldn't slow you down. It wouldn't slow down your muscles or anything. It's just that the actual speed of the ball wouldn't be like 10 kilometers per hour plus the speed of the spaceship. It would be something like much smaller than that plus the speed of the spaceship, so that it would never, no matter how hard you throw the ball, it won't actually go faster than the speed of light.
Okay.
So,
Thank you.
yeah. No matter how much energy, if you tried to shoot it out of the most powerful cannon, it still wouldn't go faster than the speed of light. It would just go a little bit faster than you're going now.
So it would like asymptote to like the speed of light.
Yeah, exactly.
So maybe I misunderstood, but in the example you just gave of your explanation of the black hole, and you said why it was wrong, and the person in the spaceship would see their friend sort of slowly moving slower and slower as they move towards the event horizon. And then basically once they've crossed, they would just kind of freeze. But wouldn't they after a while disappear? Because you're still getting new information from just beyond just on your side of this event horizon. And so once the person is not there anymore, you would get new information saying he's not there. So you would just sort of see him disappear after a while, no?
No, it would just, so it would be like the person just sort of fades away, fades slowly away. Also, the light gets redshifted because it's got to climb out of the gravitational field and so on. So the light coming
So you're
from,
seeing some frequencies, but not others.
what's that?
So you're seeing some frequencies, but not others.
Well, yeah, they'd all get shifted to lower frequencies, basically, because it loses. So all the light coming from the astronaut falling into the black hole has got to climb out. So it loses energy when it gets by the time it gets to the spaceship. So it would be like the person would, from the point of view of the person in the spaceship, the guy falling in is just going to get redder and slower, and eventually you wouldn't see him anymore because it would just be sort of asymptote to the event horizon. But on the other hand, from his point of view, just falls right in. And so, in fact, we could even be in a black hole right now. Actually, we might not even know it if it's a big enough black hole. There could be an event horizon around us, and so it's not necessarily it's not like it would be destroyed at the event horizon or anything like that. But
Yeah. All right. Thanks.
Okay.
I have a question on a slightly different note. How does the discovery of gravitational waves in general affect science on a molecular level, especially quantum mechanics? Like, are there new things that they're detecting there, or what's happening?
That's an interesting question. So So there are things you can learn about the physics of, say when neutron stars collide. There's a lot of physics in there around the material, the creation of elements and so on because of the collision. And so you have neutrons in there, and so because of they're moving very fast and they collide and so on, you have other kinds of things that are made. So that gets almost into kind of the molecular physics of this. It's more like nuclear physics, but then so you can learn that kind of physics. But then at the level of like quantum gravity, that's where you have quantum mechanics plus gravity. Right now, that I think. So there are experts in the room here who may have some ingenious idea, but I think we're not learning very much about that from the gravitational waves right now. So there's not much you could get on the molecular level of this. Although there's this idea that around the singularity, which is at the center of the black hole, where like infinite gravity and infinite density and so on, that's where quantum mechanics comes into effect. But we can't really see that right now because it's buried inside the black hole.
Okay, thank you.
I've got one for you from myself. So, and I read a paper a year or two ago that talked about these really enormous black holes that they discovered very far away. Am I right in understanding these holes may be forming from taking in mass and light, whatnot, from anything that gets close enough to them, or are they more becoming large from colliding with other black holes? And how fast are these things expanding? Is this a worry, so to speak, for us or for any planetary system in their way?
Yeah, so that's a good question. So the simple case of like a big star running out of nuclear fuel and then collapsing, that produces black holes of 30, 40, 50 solar masses, that sort of thing. Then when you get into like at the centers of galaxies, you get millions and billion solar mass black holes and really, really super huge ones. I don't know the latest on how those are formed. I don't know, Eliu, maybe you know, but there's not a really clear idea. There are different ideas about how they might form, right? But so once they're there, they are accreting more material. Things are falling into them and they do get bigger. But it's not really a worry. Like it's not like suddenly a black hole we didn't notice was in the solar system and it's getting bigger and bigger and it might swallow us up. So I wouldn't worry about that.
Thank you, Dr.
There are other things to worry about, though.
Okay, we got another question or two. I'll get another question or two.
One more question I've heard about giant black holes that are formed or exist in the center of every single more or less galaxy. I want to know the history of those ginormous black holes.
I'm sorry, could you repeat that? I didn't quite hear it.
In the center of every single universe, not universe, every single galaxy, there is a humongous black hole, and I just wanted to know how it formed, why it formed, and yeah, generally just the history of it.
Right. So I think that's still a bit of a mystery. What's the astrophysical process that led to, like, inside? Well, let's say spiral galaxies tend to have huge black holes at their cores, and so I don't really. I frankly am not an expert on this, but there are different processes you can think of. There are black holes. They sort of they coalesce. You get bigger black holes. Process that goes on for a long time. But I think there's not enough time to really create something that's so large there. So I don't know. So I'm looking at my astronomer friends here. So if you want to do a PhD in astrophysics, that might be a good topic. Nobody knows.
And another question is there a like specific number or specific diameter a black hole must reach for Hawking radiation to like not dissolve the black hole? Or does it singly depend on like what comes into the black hole, what it like eats up?
Right. So you mentioned Hawking radiation, which is this idea that there's a sort of, in the simplest terms, there's like a creation of pairs of particles, like a positron and an electron. So they're like opposite and equal. And so this happens all the time in the vacuum. According to quantum mechanics, you can get these sort of creations of particles, but then they go back into the vacuum. So there's this uncertainty principle that allows you to have these sort of violations of energy conservation, like locally. And then right at the edge of a black hole, you could have this, and one particle actually goes into the black hole and the other one gets out. That's more or less the basic idea for the Hawking radiation. So let's see. The way it works is the bigger the black hole, the slower the Hawking radiation is. I'm trying to remember. Some experts here know this stuff better than I do. And so for black holes this causes black holes through a quantum impact or quantum effect to evaporate over time. So the sort of the smaller black holes will evaporate faster than the bigger ones because it happens. The event horizon is further away. That's right, I guess, isn't it? Just trying to think that through. Yeah.
Yeah, but my question was exactly just does it depend on the original mass of the black hole? Or, for example, if a very small black hole gets to like consume a lot of mass, that like for example different planets come and that join the black hole, would then does that affect the Hawking radiation, or does it like slow it down? I don't know.
Yeah, it would. I mean, the bigger black holes will evaporate more slowly, but yeah. So I'm not sure what more to say about it, but bigger black holes. So and black holes will get bigger as more mass falls into them.
Yeah. Okay. Thank you.
And by the way, just to give you an idea, like the sun, I think the radius of a black hole, the mass of the sun is like 3 kilometers, is it, or is it 1.5? I forget, but okay. I think it's 2.98 kilometers. The mass. That's how big that's what the event horizon would be for a black hole, the mass of the sun.
I know Earth would be a peanut or something, size of a peanut.
Sorry, I couldn't hear.
I saw he said that Earth would be like the size of a peanut, and I have a question still. Back to the gravitational waves and the vibration of space-time.
Yeah.
Could you theoretically, through the vibrations of space-time, make electromagnetic induction on our planet to have somewhat of an energetic source?
Well, the thing is, the oscillations of the Earth due to gravitational waves are there, but they're so tiny that it's going to be hard to think about how to make the practical like engine out of that to create energy. I mean, it's sort of unbelievable that we could even detect them in the first place, let alone turn that into a source of energy. So I would say probably not, like theoretically, probably so, but the truth is you'd never be able to do it.
Okay, thank you.
One other question for you, Ed, because I mean, it's been really so great talking to you. I think it gives students here an idea of just the amount of cooperation between scientists around the world. And I wonder if you could tell them just a little bit about the LIGO group that actually you were part of.
Oh yeah, okay. So that's a really good point, Chris. So you might think of science like in Einstein's day, it was sitting at a desk and thinking really hard and talking to people, of course, but it's kind of a singular effort, let's say. These days, science has become extremely collaborative, and there are a lot of reasons for that because the problems are very complicated, and also it allows through data sharing. People can work together on projects because they can share data electronically. So, in fact, we're sharing data right now. Data is being sent here from NCSA to Berlin and back and forth. And so we're sharing this conversation because of shared data. And so that actually allows people to work together. And so there is a group called the LIGO Scientific Collaboration that has, I don't know how many people it has now, but it's over 1,000 people. It's probably many. How many people are in it by now, Elliot? Do you know? How many? 1,200. Okay, there are 1,200 people around the world who are in this thing called the LIGO Scientific Collaboration. A lot of them are in Potsdam at the Albert Einstein Institute. So that might be the biggest single site of collaborators in this. But they're in many countries, China, United States, most countries in Europe, Asia, South America, and so on. There are people from all over the place. And they share data. They have an agreement to share data across all the collaborations. And then they work together to analyze the data. They do simulations of the sources to say what does that look like? And now they have agreements with astronomers who are not really directly part of the LIGO scientific collaboration, but they're part of through MOUs, a memorandum of understanding. They'll share data, and so there are literally thousands of people that actually collaborate on this in this science. And there are big meetings that people get together where they talk about things all the time, video conferences, emails, and it's a very, very exciting and very social kind of environment for people to do science in.
Thank you very much. Any other last questions from my students here?
We
want to thank
actually
you one more time.
So, Chris, I want to say one other thing. We have a high school student here at Uni High, the University of Illinois High School, that's actually in the group, has actually been involved in a paper here. So 2 papers, I'm told. So, and he hadn't even told his physics teacher yet. So if any of you are doing research on the side, you probably should let Chris know. So.
Please do. Nice. Well, we're really lucky that you were able to take time out of your busy schedule to see us here at the John F. Kennedy School, your son and daughter's old alma mater. And I think it was a great experience and probably opened up a lot of eyes for a lot of my students here. They all look pretty happy. And we'll wish you a great rest of your day. You certainly started very early with us.
Thanks a lot, Chris, and everybody. And great questions. I always like doing this. So, as Chris knows, I come to Berlin whenever I can. So if I have a chance to see some of you in person, be happy to do that. And I hope you go take a look at some of these websites. Remember, scienceface.org, a lot of interviews with scientists. And then the Science of Interstellar. I would just look at that if you're interested. Kip has written this book, Scene by Scene, using basically high school mathematics, but it's really mind-bending, so it's exciting.
Super, and I will try and from your talk, I'll just take that page with the links and information, and I'll try and send it to the students who came today as well, so they have that shared through email.
Okay, good. And thanks to NCSA, thanks Michael and everybody for doing this on this side.
Yeah, thanks to everybody on your end very much.
All right.
Very well.
Bye.